Hello everyone. So today I'm going to talk to you about the morphological and kinematical properties of the sample of integral values that we have studied in the Califa survey, and how the information that we get from this study will tell us something about the formation and evolution of the systems. So we know that lenticular galaxies span a broad range of galaxy properties in terms of both the kinematics or the photometry, and so we think on this it's clear that there should be more than one formation mechanism. So here I just put two of the major formation scenarios that have been proposed for the formation of the lenticular galaxies. So we have in the top. So one term is of course major mergers at high redshift, where you have a kind of inside-out formation. And in this category we can put also intermediate or minor mergers that goes with the life of the galaxy. And we have also this second formation scenario in which this scenario is based on the idea that lenticular galaxies are the end product of spirals going through a high density environment. When then the gas is removed from the galaxy, the sun formation is shut down, and then you get the red galaxy that represents the clusters. But what is common to these two scenarios is that bulges, the central component of the galaxies, contain a lot of information, a lot of useful information to understand the formation of the systems. And this is reflected on the two kind of bodies that we think that exist in the universe, where we can divide them into a set of classical bodies that are formed in somehow by processing at high redshift by galaxy mergers, for example. And these classical bodies, they share properties of elliptical galaxies in terms of the photometry again and the kinematics. And then we have also these like bodies that are formed by internal cellular processes, maybe driven by bars or by spiral arms, and they share more properties, more kinematic and photometrical properties similar to the disk. So the idea of this study is to figure out what are the main morphokinematical properties of the bodies, try to place them into the scenario for the bodies, and then have an overall idea on the properties and the formation of lenticular galaxies in general. So for this we use Califa. We use a sample of 25 lenticular galaxies from Califa. Here I show you the distribution of the stellar mass on local galaxy density and the color magnitude diagram for our sample. In gray, this is the Califa model sample. In black, this is our sample of lenticular. And in red, we have a sample of elliptical galaxies also from Califa. So as you can see, our sample is representative only of a particular range of masses from 10 to the 10 to 10 to the 11. It's representative also of galaxies in low density environments, so galaxies mainly located in the field. And the color of the galaxy of our sample of lenticular galaxies is similar to that of the elliptical, and they lie on the read sequence of the color magnitude diagram. So keep this in mind because this will be important by the end of the talk when I will try to make the overall picture and information of these systems. But what we want to study is the bodies, the central component, and in order to understand the properties of the bodies, what we need to do is a photometric decomposition. We heard about before about photometric decomposition on Califa galaxies. This is something that we have done also within the collaboration. There is a paper which is about to be out. And what we have done is a fully two-dimensional decomposition, and an important point is that it's multi-component. So the idea is that if you want to study the properties of the bulges, the properties of the central parts, it's very important that you take into account as much as possible structures in the galaxy as you can. Since many of these structures are extrapolated to the center, then the values that you will obtain for your bulge will be strongly dependent on the model selection that you have. We have done this for all the Califa early 3, so we are going to deliver about 400 galaxies, including only the edge systems and the interacting galaxies, and the 3 is one band ER9. So using this photometric decomposition for our 25 lenticular galaxies, what we have done is obviously going to the stellar kinematics. And Maria showed this morning some fantastic maps on the stellar kinematics. These are just 3 examples for 3 different galaxies. Here you have the flux integrated from the theta cube, velocity, and velocity dispersion. And here I have plotted in black, in ellipse in black, the ellipticity, the position angle, and the effective radius of the bulge for these particular galaxies. And in these apertures where we are going to measure the kinematic quantities to measure the populational support of these bodies. And we have done this using the typical lambda angular momentum, lambda parameter, using the definition that was done by the Sauer and Deltas 3D teams. But in this case, we have not measured this lambda within one effective radius of the galaxy, but we have concentrated to the central part, to the central spheroid, to the bulge of the galaxies. With this measurement, we have plotted the typical lambda epsilon diagram that is used to study the dynamics of galaxies. And here we have the typical lines. The red line is the empirical separation between fast rotators on the top and slow rotators on the bottom. We have the black line is representative of an isotropic of the rotator model. And then we have the blue line, which is the edge-on view for given variation of the anisotropy with intrinsic shape. This was also derived by the Delta 3D team. And from this plot, we can figure out immediately two things. The first one is that all our points are over the red line, so most of our bulges are fast rotators, so they have whatever a given amount of order rotation, and most of them are also under the black line. So even if you have some rotation in our bulges, what this means is that you still need some degree of anisotropy in these bulges to reconcile the dynamics of this system with their shape. So these are the two things that you can infer from this diagram. What we wanted to do is to study the combined properties, the morphological, the photometric properties with the kinematics. And this is what we did in the following plot. Here we have the same, the lambda epsilon diagram, but in this case, the lines are the same. And in this case, what we have done is to label each galaxy, each particular galaxy, with a photometric, with a given photometric property. So in the upper panel, we have the Cerseic index. Blue is lower Cerseic index, red is high, and the same for the bulge to total luminosity ratio. And immediately from this plot, what you can see is that there is no obvious correlation between the photometry and the kinematic. There is no obvious correlation between the position in this diagram and the colors. But you can say, okay, this can be an effect as a projection can be a projection effect, can be something related to the inclination, because as you can see here, when you have the edge on view, for example, the lines, the dashed lines represent the variation of a system from the edge on view here on top of the line to the face on view here in the origin of coordinates. So what we have tried to do is to try to understand if this lack of correlation is just an inclination effect or is something intrinsic to our bodies. Of course, to get projected lambda, the angular momentum, we need to have access to the anisotropy and to the intrinsic shape of the bodies. And observationally, we have not access to this data. So what we tried to do was do a statistical approach. And let me explain you a little bit what we did for this. So basically, let me remind you what is in this plot. This is the lambda epsilon diagram. In this case, what I have plotted is just lines of constant anisotropy for the edge of view of a system. So here is the line of an isotropic of the rotator, and then when you increase the anisotropy, you move from left to right. But if you pick only one anisotropy, in this case, then you have that for each intrinsic ellipticity, you will have all the variation from the edge of view to the face on view. So what we did is, for each particular bulge, we computed all possibilities for the anisotropy and for the intrinsic shape. We deproject our value of lambda in this statistical way, and then we look for correlations between the deprojected angular momentum and the photometric quantities, the Cerseic index and the V over T. And this is what we get out of this. So here is the distribution of the Spearman correlation coefficient. In this panel, what we did is look for correlation between the deprojected lambda and the Cerseic index. In this panel here is with the V over T, the bulge to total luminosity ratio. And what you can see here is that there is no, well, this is the Spearman correlation coefficient, so 1 is a positive correlation, -1 is a negative correlation, and 0 is not correlation, of course. So what we have here is that there is no negative values for the Spearman correlation coefficient. So basically what this tells you, this is what you would expect. For example, if you have a population of bulges, which is a combination of classical and pseudo bulges. If you have a classical bulge, they should be more centrally concentrated and dominated by pressure. If you have this-like bulges, they should be more like this, so lower Cerseic index and larger rotational support. But this is not what we see here. And in any case, when we only have positive values for this correlation coefficient, they are very weak. They are only less than 0.5. So what we can tell from this is that this lack of correlation is not dependent on inclination effects in the lambda epsilon diagram, but is intrinsic to our bodies. And then our explanation for this could be that in our sample, most of the bodies, or at least most of the bodies which are driven this kind of correlation, they were formed by major mergers. Why that? This is because when you have a major merger or even other kind of merger like minor or intermediate, the relation between the bulge growth and the change in the angular momentum depends on many characteristics of the merger. It depends, for example, on the orbits of the merger, if they are retrograde or they are prograde, and depends also, for example, on the gas fraction of the progenitor galaxies. So this lack of correlation can be a hint that most of the bodies that we have in this sample, they are actually created by mergers somehow in the universe. And this is also somehow in agreement with what I told you at the beginning of the talk about the global properties of our lenticular galaxies. Remember that our sample was representative only of high stellar massive galaxies which are red galaxies in the field. So the scenario of fading, of creating the lenticular galaxies by fading as spirals, is not what you expect from galaxies in the field, and in fact this is not what we found. What we found is that even if galaxies are fast rotators, they need some anisotropy, and then what we get is that the photometric and the kinematic properties of the bodies were not related, and we assume that this is because of merger history of the galaxy. And that's all.
Okay, we have time for one question. Wow, surprising.
Hi, thanks. I'm a bit confused because you have a sample of galaxies which are probably looking very different from each other in terms of the bulge to total ratio, inclination, and so on. And also the radial extent, what you call the bulge, depending if it's very central or very extended as compared to, let's say, 1 RE of a galaxy. So I would propose a test which is probably not very difficult to do, considering the number of galaxies you have to deal with, which is just to do a very simple dynamical model for each of them, to project them, look at them edge on, and do the same exercise. It's probably taking a few hours. The tools are there. And my guess, my naive guess, I may be completely wrong, is that because you are mixing many different structures at different scales, mixing the disk and the bulge, what you call the bulge, in this you basically destroy any correlation whatsoever you could find, which doesn't necessarily put your conclusion at odds with what is the reality. I mean, maybe you're absolutely right there, but what I'm saying is from the data, I would say that most of the scatter will come from this confusion. I don't know if you would agree with that, or what's your perspective on this?
Well, I agree in the fact that, of course, dynamical modeling will be the next step if we want to be sure about the results. We did some tests about to check the contamination that we have from other components, especially from the disk. So we, for example, compute how many light we have in one effective radius of the bulge compared to the disk inside this same aperture, and the contamination was very low in terms of light, of the photometric composition. And then we did also some tests. I have here one plot, for example. This is again the lambda epsilon diagram, and here where we have plots in blue, the blue stars are the disk. So we compute the angular momentum at 2.2 scale lengths of the disk, and then connect each galaxy with the bulge. And we have that most of the disks are here in the region of isotropy, so they has higher angular momentum than our bodies. So in the case that we are contaminated by the disk, this is still an upper limit, so our conclusions are still there. So this point should be still lower than this in any case. We can do it.
Okay, I think you can continue later. We don't have time for much more questions. So next speaker.